Look at this July 4th, 2026 edition of the MY Artificial Intelligence Scientific Research Daily. This single document gives us a clear roadmap for where the bleeding edge of computer science is heading right now. Today's issue highlights 19 new papers that cluster around 4 main tracks: complex agents, evolving benchmarks, embodied AI hardware, and continuous security systems. When you look at these projects together, a specific trend emerges. These 19 papers represent a collective push into the real world, moving away from isolated, perfectly controlled sandboxes and into chaotic, long-term applications. For developers, this means the old metrics are losing their utility. High scores on traditional benchmarks tell us almost nothing about whether a model will fail when you leave it running in a production environment for an entire week. AgenticDataBench forces data science models out of basic Q&A loops into 15 vertical domains, including real-world financial tech. It measures the process quality of individual skills, like data cleaning, so engineers can pinpoint where a model trips up before reaching a final answer. We see a similar push in AgenticSTS, which drops AI into closed-rule, highly randomized game environments with a strict constraint. Instead of letting the model read an infinitely growing chat history, it operates under a limited memory contract. Every turn starts fresh, forcing the agent to actively retrieve only the information it actually needs to survive. Then there's ReContext, a technique targeting massive 128,000 token context windows. When documents get too long, models lose track of facts buried in the middle. Rather than retraining the entire neural network, ReContext filters out irrelevant noise, creates a concentrated pool of actual evidence, and replays it right before the model generates its final answer. What all of this shows is that raw context length means very little for enterprise systems. If an AI cannot actively manage its own memory state, pulling forward what matters and discarding outdated facts over a long timeline, it will eventually hallucinate and collapse. This shift toward maintenance is why TestEvo-Bench was built. In real software engineering, as business code evolves, tests must evolve with it. This benchmark evaluates models by making them co-evolve test scripts alongside 152 real Java projects, grading them on strict technical metrics. That emphasis on safety boundaries brings us to UnderSpecBench. The researchers here proved that when coding agents are given vague DevOps instructions, they don't stop to ask clarifying questions. Instead, they often guess the user's intent, leading them to execute dangerous, out-of-bounds actions on servers and repositories. Keeping these evaluations reliable is another massive hurdle, which MMBench-Live is solving with continuous updates. Once a test is public for too long, AI models inevitably encounter the answers in their training data. So this team built a pipeline that autonomously generates fresh, unpolluted questions to keep multimodal leaderboards accurate. The takeaway here is definitive. Stagnant leaderboards are losing their relevance. If a benchmark isn't directly executable and constantly updating itself, it cannot measure whether a model is ready for a production environment. Program as Weights feeds a plain English request into a compiler, generating a lightweight adapter. This adapter plugs into a small interpreter to execute a fuzzy function. By compressing instructions into weights, developers achieve massive model performance using 1/5 the memory on a local machine. This need to track ongoing states appears in video generation as well. WorldDirector solves a major flaw in AI video, where objects seemingly disappear from existence if the camera pans away. By introducing a persistent dynamic memory, the system maintains the exact identity and state of objects perfectly, even off-screen. We see this exact division of labor translating into physical robotics through a project called TAP. Instead of needing millions of highly expensive human demonstrations to teach a robot how to move, the machine first learns basic physics and motor skills by freely exploring its environment using unlabeled play data. Only after it understands how to physically operate does it ingest a tiny amount of expert data to learn specific tasks. Whether we are talking about compressing logic to run on a local laptop or teaching a robotic arm to understand its own physical limits, the industry is decoupling high-level reasoning from physical execution. This separation allows developers to bypass the strict hardware limits of edge devices entirely. As autonomy increases, security risks escalate, bringing us to a paper on distributed attacks in continuous state AI. The study reveals bad actors can fracture a malicious payload into tiny, harmless microedits. Over a long session, the AI slowly builds out an exploit piece by piece. Because no single edit contains the entire attack, traditional code reviews that only look at one step at a time are completely blind to the larger threat. An auditor checking the daily log will see a series of innocent updates and entirely miss the cross-turn behavior being orchestrated. The required countermeasure is outlined in a parallel paper on online safety monitoring. The system establishes strict risk thresholds that operate continuously while the code or text is actually being generated, allowing the system to interrupt or downgrade the AI's permissions the moment an anomaly is detected. Static input filtering alone is no longer enough to secure our infrastructure. The moment models are granted the autonomy to execute multi-step workflows, our security protocols must shift to continuous, active behavioral auditing. Look at the editor's comprehensive judgment. The field is coalescing around two concepts: executable evaluation and long-term state. From adapting Java tests to security monitors hunting distributed attacks, these tools serve one function: identifying an AI's boundaries, flagging data pollution, and categorizing real-time failures. The era of the single-step prompt is closing. Engineering teams are now building systems to manage the continuous variables of the flow of time.